So hi everyone, I'm very glad to present my work to you. My name is Hanqing, come from University of Twente, and so the topic I'm going to present today is detecting selective sweep with using FPGA-accelerated spiking convolutional neural networks. So there are 6 parts in this talk. So I will start with introduction, and then I will briefly introduce some background, and then I will discuss our ICN architecture in method. After that, I will show some results of our ICN compared with other deep learning based method, and then we go to conclusion. So positive selection is a process that the new advantageous mutations occurs in a population, and the individual with these mutations will have more chance to leave offsprings than others. So the positive selection determines the direction of the evolution because the individual carry this advantageous mutation will have more chance to survive. And recently, that positive selection is also evident in variation of viruses like HIV, like influenza A viruses, and very recently, it's also been found in SARS-CoV, the coronavirus. So the current method that's based on deep learning method to detect positive selection is mainly like first the summary statistic based method, which they calculate the summary statistic and then convert them in colorful images to feed the CNN to all other deep learning method to do classification. And then another is a raw data based method. They directly apply AI method on the raw genetic data to do the classification. Although those deep learning based method achieve promising results with summary statistic based method, but they still have drawbacks. The most of existing deep learning based method that they required the entire raw data to train the model, which could lead the long execution time and also the scalability issues when the window size increase. And also the volume of the real data also requires more computation demands. The summary statistic-based deep learning method, they can process the different window size data, but they can be distorted easily by confounding factors. So in order to deal with scalability issues and also to deal with confounding factors, here we present our ICN's architectures. So before we go to the CNN architectures, I will briefly introduce some background. So what is a selective sweep? When the population's positive selection occurs in a population, it will leave trace the selective sweep in the population. So due to the genetic hijacking, the genetic diversity in the neighbors will be swept away. So here, each row represents a chromosome, and each column is a SNP. The white circle represents a neutral mutation, while the the black circle represents advantageous mutations. So when this advantageous mutations occurs in this population, it will spread over generation, and finally, every individual will carry these mutations. So when positive selection occurs in the population, it will leave some distinct signatures in the genome, like a U-shaped site frequency spectrum, a distinct pattern of linkage disequilibrium, and reduced genetic diversity in the neighbors. So before we go to depth, there are some basic, I will briefly just introduce this basic concept. So allele frequency refers to how often an allele appears in this population. It could be calculated by the number of copies, the number of certain allele in this population divided by the total number of the genes. And the set frequency spectrum is describe the distribution of the allele frequency of a given site. So here, the left images show the SFS of a neutral region. We can observe that it shows a smoothly decreasing trend. And for the selected regions, it shows a shift towards a low variant to high variant, which is more like a U shape. And the linkage disequilibrium is a non-random association of alleles at different loci. So here, when the positive selection occurs, the SNPs on the same side to the favored allele will have high LD, while the SNPs on a different side to this favored allele will have low LD. Then there are some AI method. That's first convolutional neural network is a kind of ANN that use convolution at least in one of its layers, and normally it consists of two stages, feature extraction and classification. And spiking neural network is a kind of artificial neural network that's more closely mimics the natural neural networks. So here, the input from the previous layer will be the output from the previous layer will be the input for the spiking neurons. And when based on a threshold, the spiking neuron will emit a spike to the next layers. So here on the right figures, each spin node point represents spiking neurons, and the spiking neural network is a set of spiking neurons connected with each other. So the spiking convolutional neural network is a deep learning neural network that comprises of standard convolutional layers, but it also has the past feature maps to the spiking layers. So the spiking convolutional neural layers networks, like it has convolutional layers and also spiking layers. So I will briefly introduce the FPGA because we finally deployed our CNN, our neural network on the FPGA. So field programmable gate array is a kind of a configurable integrated system for the special computational intensive tasks. So compared with a general CPU or GPU, it's more flexible. And because there are a lot of logic elements on the board, it could do parallel processing. And because it's deployed with hardware directly, so it has low latency, and it's highly custom design. It has lower power consumption compared with general GPU or CPU. So before we feed the images to our SCN, first we did the data preprocessing. First, the data represented in binary, like in MS file, will be converted into grayscale images first, where 0 represents the ancestral state and the 1 denotes the derived state. So then we did a pixel rearrangement to help our SCN do the classification, and we investigate this data rearrangement algorithm in our previous work, and we found that it could help CNNs to do better classification. And here is an overview of our spiking convolutional neural networks. So our SCN consists of one convolutional layer and two spiking layer, two fully connected layer. So first, the output of the outcome of the computational operations will be the input for the spiking neurons here, and when this potential is more than the threshold, the spiking neurons will emit spikes to the next layer, to the fully connected layers, and then the outcome from the fully connected layer will go to the second fully connected layer, and finally we'll have two spiking neurons to do the final prediction. So here is how our ICN do the inference. So first, we processed 5 rows of the input images and treating them as a single time step. So, and then we can observe we get the hidden neural spikes from the input. And after that, we have 2 neurons, spiking neurons to do the classification. And then we repeat the process until we process all the images. As we treat the rows as a single time steps, so this enable us to do the early stop inference. So this criteria is determined by the difference in the firing counts of 2 output neurons. So when the fire count of the one neuron surpass another by a margin that exceeding this threshold, we consider that this corresponding class of the more active neurons will be selected as a prediction outcome. So this early stopping inference allows us to utilize less time steps, which means we process fewer rows to achieve the accurate classification. So here on the the left figures show the potential of the outcomes of 2 different neurons. Here, on the right images figures, we can observe that at the time steps of 46, we observed that the one neurons, the firing count of one neuron surpass another. So here, when we set the early stop point with a threshold at 7, we can observe the final prediction result at the time step of 46, which means we only process 46 rows of the images to observe the accurate classification result. So after that, we deployed our ICN architecture on hardware accelerator. So here we train our ICNs on an ARM processing systems, and then we load our ICNs, the weight of our ICN on the programmable logic via connection links. So we compared our ICN with others deep learning based method for identifying selective sweeps. Yeah, so here is our experimental setup. We have we simulate 8 data sets, and from data set 1 to 6, we have the classic selective sweeps. And for data set 7 and 8, we only have the recombination hotspots. So for our simulation, each of our simulations can have the sample size is 128. We extract 128 SNP from center of each simulations to generate images. So for each data set, we have 1,600 images for training site, 400 for validation site, and 2,000 for testing site. So our ICN architecture is implement on the framework of Keras and TensorFlow. Then we deployed our ICN on the platform of Pink 7020 and another FPGA board, Keras K260. So here first we compared our ICN architectures with other CN architectures for image size of 128 times 128, and from this table we can observe that we only have 3 layers, which is a shallowest depth among all the CN architectures, and we have like 80,000 trainable parameters, which is a median amount of parameters among all the architectures. Although we have like 80,000 parameters, but we still is the second smallest model size because the precision of our network is only 8-bit. So then we compared our SCNs with another CNN method, the SweepNet, for classification, for identify the positive selection under different genetic scenarios and using the entire sample size. Although we observe our CNNs show some drops for specific datasets, for most datasets we observed comparable or even a little bit higher accuracy than SweepNet. And here we also evaluate our SCN with using early stopping inference. So here, the y-axis on the left figure, the y-axis is represents accuracy, and the x-axis represents the early stopping threshold. So here we could observe that when the early stopping threshold is 9, we can achieve the maximum classification accuracy for each data set, which means, yeah, so here the average early stopping rows for different data set is range from 43 to 125, which means we can only process 43 to 125 rows to achieve the maximum classification accuracy instead of processing 120 all the rows of the images. Then we also compared the accelerator performance. So here, first we compared our SCNs deployed on the pink on two different FPGA against the SweepNet deployed on a general CPU and GPUs. Here, we observe that we can when our SCNs was deployed on the Keras K260, we observed the throughput of almost 1,500 images per second, but with way lower power consumptions compared with the SweepNet deployed on a CPU, on a general CPU or GPU. And then we also look at the detail of our resource utilization of our board. So here we observe that we almost make full use of our BRAM, which is memory on chip. So this is also the limitation for us to gain the improvement so far. Okay, now we go to the conclusion. So, to our best knowledge, it's the first time that we use SCN for classification of adaptive genomic regions for the first time, and we utilize an early stopping inference, and we could achieve accurate classification accuracy with only processing fewer rows of the images. And our FPGA-accelerated SCN architectures, we observed 3 times and 45 times speed up compared than a SweepNet, which is another CNN-based method deployed on a GPU and CPU respectively. So for the future, what we can do is that we can do a NAS neural architecture search to improve our SCN architectures. And then so far, we just use a cheap board with a limited resource. So we are going to use larger FPGA for acceleration. And we could also integrate our SCNs with detecting tools for the detection of selective sweeps. Okay, thank you. That's all my presentation.